So today we are talking about Ising model. Okay, it's the last new subject in the course. Okay, so the Ising model is a model that describes a lattice. Okay, so if we have atoms in the lattice, and the atoms have interactions between them. Okay, so Ising model come to describe this lattice. So the assumptions of Ising model. So we assume here that not every atom interacts with every atom. We're assuming that, let's say we have the lattice. So we assume that the interactions are limited with distances. So, for example, we can do an assumption that only nearest neighbors are interacting with a specific atom. So, if we're talking on this atom, we assume that only the nearest neighbors to the atom interacting with this atom. Okay, so the Hamiltonian of this lattice looks like some interaction energy, and then we're summing on all interacting atoms. So SISJ is some quality of the atom in the lattice. Usually we will talk about spin. So this will be spin of atom I, and this will be the spin of atom J. And we're doing this summation only on I and J that are nearest neighbors. Okay, and if we have an external field, so we can insert its influence as well in the Hamiltonian. And this is the Hamiltonian of Ising model. Okay, so how we describe the state of the lattice? We're using what we called an order parameter. Okay, so we write it as M. This is our order parameter, and it says how much the lattice is ordered. So if the lattice is in random state, some random state, so without any considering the energies, so we can expect that 50% will be with spin up and 50% with spin down. So this is a totally random state, and then the order parameter will be equal to 0. Okay, if we in totally ordered parameter, so if all the spins are up or all the spins are down, so order parameter will be equal plus minus 1 plus 1 if all the spins are up, and minus 1 if all the spins are down. So the order parameter is actually the average spin in the system. Okay, so indeed, if we are in random state, the average spin is 0, and if we are in ordered state, the average spin is +1 or -1, and all the middle states we can get between this random state and totally ordered state. So the order parameter graph, we can draw it as something like this. So if we have here +1 and -1, and we will draw it as a function of the temperature. Okay, so we're expecting that for high temperatures, we won't get any affection of the energies on the states of the spin. So we'll get totally random state. As we decrease the temperature, we expect that the system will go to its minimal energy state. So let's ignore the outside field term and just look on the interaction. So we will get minimal energy if all the spins will be in the same direction. So at 0 temperature, we will find the system in ordered state, or +1 or -1. And for high temperatures, we will find it at, let's use another color. So we'll find the state in its ordered state. So the total graph will look something like this. As we go high in the temperature, the system goes to a random state. Okay, so we can point at this point and call it the critical temperature and say, okay, we have a phase transition in this point. So above this point, we're in a random state, and below this point, we're in an ordered state. So we have here some phase transition. Okay, so let's see it in the math. Okay, so to reach this graph in mathematical way, we need to describe the average spin in our system. So we will have this graph. Now we have interaction in the system, so first we want to do some tricks to separate this interaction, to separate those spins, so we can write the partition function for the whole lattice using the subsystem partition function. Okay, so the second assumption of the Ising model . Okay, so we're saying, let's assume that the spins are close to the average spin of the whole lattice. Okay, so we can say the average spin the spin of atom J will be equal to the average spin of the system with a small change. Okay, we're assuming that there are only small changes from the average spin. Okay, so this small change, we can write it as the real value of the spin minus the average spin of the system, the order parameter. And then, under this approximation, so this is the mean field approximation. Right, so you did it in the lecture and you saw that we can write this summation on the spins on nearest neighbors as m number of nearest neighbors, and we're summing on a single spin in the lattice, and we have here some constants. So we have m squared number of nearest neighbors times number of atoms divided by 2. Number of nearest neighbors. So this will change, depends on the model you want to take into consideration. Okay, so if we're taking this approximation and insert it to the Hamiltonian, and again let's take without external field, just the interaction. So we get that the Hamiltonian equals to minus j times this sum. So we have m, z, and n, sum from I equal 1 to n, si minus this constant m squared, z and n times n divided by 2. Okay, and now we don't have any interactions in the Hamiltonian. So we can write the contribution of to energy of one particle in the lattice. So we can write, okay, for one particle the energy will be minus j m z and n and the spin of this atom plus m squared z and n and j divided by 2, and this is the contribution to the energy of one atom in the lattice. And then we can write the subsystem partition function for each atom. So we can do it now because we don't have any interactions in the energy between the atoms. Okay, so the subsystem partition function for one atom, right? It's the summation on E minus beta epsilon on all possible states. So for this case, all possible states is spin plus 1 or spin minus 1. This is the states of one atom. So we have here Si equals to plus minus 1. Okay, so we will get 2e minus beta m squared z and n big N j divided by 2, and hyperbolic cosinus of beta j m z and n. Okay, so we have here some constant and we have here the dependence on the temperature. Okay, and now we have the partition function, so we can calculate the average spin for each particle, for each atom in the lattice. So now we can write, okay, the order parameter equals to the average spin of some atom I. And this equal, okay, so we can derive this from the partition function with derivatives, but we here only have two possibilities for state. So we can do it directly with the formula of average. So we want to sum up on, let's say, probability to a spin Si times the value of the spin. And we're summing on our both possible states, Si equals to plus minus 1. Okay, and then if we do this thing, we're getting that this order parameter equals to hyperbolic tangents of beta j m z and m. Okay, so we have both m in the left and the right hand of the equation. We have משוואה סתומה. So we won't solve it analytically, but graphically. So we want to see how the solutions looks like. Okay, so first, let's say the hyperbolic tangents is we want to make it simpler. So let's say these whole parameters, let's call them x. So x equals to what we have there, beta j mz and n. So we get the equation of hyperbolic tangents of x equals to m, so x divided by beta j z n m. Okay, so the solutions for this equation is when this graph and this graph are intersecting one each other. So, okay, let's draw those both graphs. Let's do it here so we have more space. Okay, so we have the hyperbolic tangents that now will be easy to draw. Just a regular hyperbolic tangent, so it looks like this. This is +1 and this is -1. Okay. Now let's go to the right hand side of the equation. Okay, so now we have here a linear graph, but we have here dependence on the temperature. So for high temperatures, let's write it as high T's. So beta is small, so the slope of the graph is steeper. Okay, so we will have a line like this. Okay, so this is for high T's, and we see we have one solution to this problem at x equals 0. X equals 0, so the other parameter also equals to 0. Okay, great. So far so good. What happens for low T's? Okay, so we get, let's say, something like this. Okay, now we have 3 solutions for this type of T's. Okay, so we have m equals to 0. Okay, but this will be a non-physical solution, so we don't use this solution. And we have 2 more solutions that are symmetrical in the plus region and the minus region. We have 2 solutions of m equals plus minus something. Okay, and so the highest value m can get from that we can see from this drawing is this plus minus 1, the ordered phase. And we see from here that we will get actually the graph we got from before, the graph of the of the order parameter with the critical temperature. Okay, how we find this critical temperature? So this will be the line with the slope that exactly tangent to the blue graph in the x equals 0 point. Okay, so the green line in the critical temperature is tangent to the blue graph at x equals 0. So we can calculate the slope of this tangents, hyperbolic tangents in x equals 0, and compare it to the slope of this line, and then we can get the critical temperature. So the critical temperature Tc will be equal, we will get J times the number of nearest neighbors divided by Kb. Great. Okay? Good. So let's move to exam question. I know what, let's just write it from the beginning. This is from 2015. Okay, so we have given two-dimensional lattice with n cells each cell can either be empty or occupied by exactly one atom. There is an interaction between nearest neighbors cells with a negative potential of minus k, and the chemical potential, אפשר שלא להיכנס?
אני כבר הכניסה.
אין בעיה. תודה. Chemical potential mu, so the Hamiltonian of this lattice H equals to minus k sum on nearest neighbors of Bi, Ej plus mu sum from I equals 1 to n Bi. So bi equals to 0 or 1, occupied or unoccupied. Okay, so we have here something that is very similar to Ising model, right? The Hamiltonian is like the Hamiltonian of the Ising model, and we have nearest neighbor interactions and so on. But only one thing, that the cells are not getting the values -1 or +1, but the values 0 or 1. So we want to take this model and convert it to something that will suit us to Ising model. So the first thing we want to do is to find the transformation between Si equals to -1, 1, between the Ising model to this model. So Bi equals 0 and 1. How do we convert those B's to S's? Okay, so we need to go from Bi equals 0 to Si equals -1, and from Bi equals 1 to Si. No, sorry, this is 1. 1 and 1. Okay, so we can write okay, we can take Bi, do -1/2, so we will get here -1/2 and here +1/2, and then multiply by 2, and then we get this transformation. So this will be equal to Si. Or we can, okay, so this is our transformation, and then we can write it in the opposite way, so we can convert from Bi to Si. So Bi equals to Si +1/2, sorry, +1 divided by 2. Okay, so we find the transformation between our model to the Ising model. Now we can take this transformation, insert to the Hamiltonian, and see what we get in the terms of Ising model. Okay, so now we want to substitute the expression found in part A into the Hamiltonian and compare to Ising model. Okay, so let's see what we will get. Okay, so we have the Hamiltonian. Okay, so we're starting with just take this value and insert it to Bi and Bj. Okay, so H equals to -k, we have the summation on nearest neighbors, and then we have the Bi and the Bj. So we have Si +1 divided by 2 times Sj +1 divided by 2, and okay, we have this standalone summation. So we have form I equals 1 to n of si plus 1 divided by 2. Okay, let's first look on the more complicated summation, this one. Okay, so what we have inside the summation, okay, so we get minus k divided by 4. Let's put it outside the sum. We have summation on nearest neighbors, and then we have si times sj plus si plus sj, right, plus 1. Okay. Great. So, okay, we have a standalone summation on si and sj. We can replace the indexes. It's we don't interested in the indexes. It's standalone. We can just replace it. So we get minus k divided by 4. So we have sum on nearest neighbors on the interaction si and sj that we know how to deal from the mean field approximation. And then we have here, okay, let's do something like this. We have two sums on nearest neighbors on si, okay, took si and sj. And then we have sum on nearest neighbors on just the value 1. Okay, great. Okay, so let's start from the easier to the hardest. Okay, so sum on the nearest neighbors on the number 1 will just give us the number of nearest neighbors. Great. So we have here number of nearest neighbors. Number of nearest neighbors times the number of atoms in the lattice. For each atom, we're summing on the nearest neighbor. Let's deal with it later. And this is, we know from the mean field approximation. So this equals to, let's see what we got here. Okay, let's just keep it that way for now. And let's see what is sum on nearest neighbors on si. Okay, so we can divide this sum into two sums. So one we will go over on all atoms in the lattice, and in the other we will go on every nearest neighbors for this atom. So we have something like this. So we're summing on j atoms, that is nearest neighbors to I. Okay, and we're summing on all i's in the lattice. So from I equal 1 to n. On si. Okay, so this summation will just give us the number of nearest neighbors. So this equals to number of nearest neighbors, summation from I equals to 1 to n on si. Okay, let's see what this gives us in the Hamiltonian. So now h equals 2, and we have the interaction. So we have minus k divided by 4, and we have this summation. So sum on nearest neighbors, si, sj. this is 1. Second, let's take these terms. So we have plus. So we have this 2 times z and n, summation from I equals 1 to n si. We have this constant, and we have this external field value. So we have plus mu, and we're summing from I equals 1 to n on, let's say, si divided by 2 plus half. Okay, so from this half, we will get just the number of the atoms in the lattice. And then we can combine this summation with this one. So we will get minus k divided by 4, and we get in the interaction SI, SJ. And then let's collect those values with the summation of SI. So we have, let's see, 2z and n plus mu divided by 2, and sum from I equals 1 to n on SI. And then we have the constants. So we have plus nz and n plus mu n divided by 2. I forgot this minus k divided by 4. Let's add it. So we have here, right, k divided by 4, and we have here k divided by 4. Okay, so we have here minus k z and n divided by 2, and we have here minus k divided by 4. Okay, so now we can look at this solution and say, okay, now we can write the Ising models, the Ising model values using our model values. Okay, and then we can just take the solutions from the model Ising and insert those values instead. So our interaction energy J will be equal to k divided by 4, and the external field value, so this will be the external field value, the value before this summation on the standard on SI. So our H will be equal to minus kz and n divided by 2 plus mu divided by 2. And this constant we don't have in the Ising model, but it's just a constant energy inside the Hamiltonian, and we don't care for constant energy. So we can just neglect this value. We don't need it. Okay, so in every question in lattice with interactions between the atoms on nearest neighbors, so we can just take it to Ising model. Okay, we can do this transformation to see how it behaves like Ising model, and then use the solutions of Ising model to analyze our model from the question. Okay, any questions?
זה שאלה שהייתה במבחן?
כן.
אוקיי. אבל אחרי שאני מגיע כאילו לסכימה, כאילו למלחמיה שלי, אני צריך לפתור אותה. כאילו להגיע, נגיד, מה הם ישאלו אותי?
זהו, אז זה תלוי מה ישאלו אותך. בעצם ברגע שאתה מגיע לגדלים האלה, אז אתה משתמש באותן תוצאות של מודל אייזינג. אוקיי, אז ברגע שאתה מגיע אוקיי, יש לך פה מקדם כפול האינטראקציה ושדה כפול הסכימה על השדה. אז אתה כאילו לוקח את התוצאות ממודל אייזנק, אתה יודע מה הטמפרטורה הקריטית, אתה יודע, זה מה שיש שם, טמפרטורה קריטית, וזה בעצם פותר לך את המודל. מה שכן, לפעמים יהיו שאלות עם אינטראקציה של שכנים קרובים שהיא קצת יותר מסובכת משכנים קרובים, אז לדוגמה...
בהרצאה זהו, עדיין לא דיברנו פשוט על השכנים הקרובים, אמרנו שהאינטראקציה היא בין כאילו כל חלקיק וחלקיק, פשוט עשינו את זה בצורה כזאת.
הבנתי. אז נניח יכולים להגיד לך, אוקיי, יש לך אינטראקציה במקום רק בין שכנים קרובים, אז נניח ייתנו לך איזשהו רדיוס, אם נניח זה יהיה איזשהו רדיוס A, אז נכון A שורש 2, ואז יכולים להגיד לך, אוקיי, האינטראקציה קורית בתוך רדיוס של 1.99A נניח, ואז אנחנו מציירים את המעגל מסביב, שבעצם כולל לך את כל השכנים הקרובים האלה, שזה גם כבר תלוי מרחק, אז גם יהיה צריך, יכול להיות שתהיה אנרגיית אינטראקציה שונה לפי מרחק, וזה גם כולל יותר שכנים קרובים. אוקיי? אבל בסופו של דבר אתה מגיע למילטוניאן של איזשהו קבוע כפול האינטראקציה, פלוס משהו של השדה, וברגע שאתה מגיע לצורה הזאת בעצם אתה מסודר.
כן, אבל הסכימה על ה-nearest neighbors, כאילו איך זה ישנה לי את J? אם אני עכשיו נגדיל את הרמז?
אז יכול להיות שפשוט המקדם שלך ישתנה, יכול להיות שנניח פה יהיה לך איזה אנרגיית אינטראקציה אחת ופה אנרגיית אינטראקציה אחרת, אז יהיו לך שתי סכימות על אינטראקציה אחת מכל סוג, אבל עדיין הקירוב של זה של מין פילד הוא יראה אותו הדבר ברגע שיש לך את הצורה. אתה פשוט תעשה לכל אחד בנפרד, אבל עדיין יש לך את הצורה של זה. בסדר?
כן, אפשר שאלה שלא קשורה?
כן.
לגבי עיבוי בוזר איינשטיין?
כן.
אז הייתה תוצאה שהגענו לה בהרצאה, שבגלל שזה מופעל על ידי הפולינומיה, מולטי פולינומיה.
אוקיי.
אז בגלל שהיא מוגבלת ב-1 ל-2.612 איזשהו ערך מסוים, אז אנחנו מקבלים שאנחנו כביכול לא מוצאים איפה הנקים שם, ואז מגלים שזה בגלל שזה מתפוצץ למטה. אז אני לא מבין, כאילו, מה בדיוק, אני מבין שכאילו אנחנו מקבלים שהפונקציה הזו מתבדרת בנקודה שמיו שווה לאנרגיה, כאילו לאפס, אבל מה זה הערכים שהם לא נקרא מצבי יסוד? כאילו אם לא, כאילו עדיין יש לי שם הסתברות שיצאו חלקיקים?
מה הערכים עבור מיו שונה מ-0 או עבור מיו שווה 0 מה הערכים של...
לא, כשמיו שווה 0 אז זה מתבדר וכל החלקיקים יורדים.
אז זה סבבה. אוקיי, אז עבור מיו שונה מ-0 זה הופך להיות הרבה יותר מסובך, עם פתרון הרבה יותר מסובך, וזה נמצא בקורס סטטיסטית מתקדמת. אם תעשה תואר שני, אז יש את הקורס המשמח. מכניקה סטטיסטית מתקדמת, וזה פשוט מפורט שם, זה באמת מקרה הרבה יותר מסובך נעשה. כן, כאילו, כן, זה ממש באמת שאלה בפני עצמה וממש נושא בפני עצמו. כן, בהחלט.
יהיה תרגול חזרה לפני המבחן?
אז ככל הנראה את התרגול של שני הבא לא יהיה חומר חדש, אני פשוט אעשה אותו כתרגול חזרה למבחן.
כאילו שני עוד שבוע.
כן.
כי אחרי זה כבר טיפה אלו.
נכון, זה כבר, כן. זהו, העניין הוא שהוא מאוד קצר, כאילו זה ב-45 דקות. יש זמן לפתור שאלה אחת, אז יכול להיות שמה שנעשה זה שנניח אני...
אפשר להיכנס?
כן, אפשר להיכנס. אפשר שנעשה זה שתואר גם יעביר תרגול חזרה, ואז הוא יעביר שאלות מסוימות, זהו, הוא יעביר שאלות מסוימות, ואני אעביר שאלות אחרות.